Okay.
So,
Mike?
audio? Okay. I'll do an intro for you.
Sure, sounds good, man.
If you guys can take your seats, please, we're going to go ahead and get started with the next speaker. Is that later you can go back and sync up all the video. Well, right now we've got live streaming, and when it's all production cut and recorded, there's going to be a zoom in on the speaker and the slides, because we're really trying to make this something that Cincinnati can be proud of. But since we don't have a cupboard, Brett simply has to give everybody a clap like that. So for this next speaker is actually the one that I'm personally and most excited about today. I think that Coleman Kane is simply one of...
I said you're too kind.
Oh, yes. Is simply one of the brightest people in the Cincinnati security community. Anybody that not only has a profile at freebsd.org for, at this point, over a decade, you don't even look that old, but also has commit access, is someone to be reckoned with. So it's my great pleasure to introduce my friend Coleman Kane to talk about Malware DNA. Let's put our hands together, please.
All right, thanks a lot, Liam. So, as Liam said, I'm Coleman Kane, and I'm going to talk to you today about a project I've been working on. I actually work for GE Aviation here in Cincinnati. We have a relatively good-sized security team that's dedicated to IT security. We fight a lot of kind of your advanced threats. That's typically what it's called in the media. And we do a lot of really cool stuff. So one of the things we do is comparing malware samples via code. And that's the method I'm using to do that is what I'm going to talk to you about today. So a quick introduction about me. And I'm glad that the cutoff happens at the exact right spot on this slide. So I am the Cyber Intelligence Programs Manager for GE Aviation. And basically what that means in short is that I'm in charge of all of our projects that collect, archive, organize, and analyze all of the things that we see, that we want to see, that type of stuff, anything that we can collect from the internet. Some of you who went to the Digital Forensics Working Group, we kind of likened it to information hoarding, and I think that's a really great analogy. I live here in Cincinnati, and as I said, GE Aviation's headquarters is also here in Cincinnati. It's actually a lot of us work at the plant site that many of you might have driven from if you were driving down I-75 this morning. Like, I'm a UC grad, so you're at my alma mater right now. Looks a lot different than it did when I went there 10 years ago. I like to go on hikes with my daughter. That's one of my favorite things to do. I have a little 4-year-old. She's wonderful. Looking forward to the day when I can bring her to DerbyCon and do the lockpicking. She will love that. I also fancy cats. You'll notice that is probably going to be a theme that you'll see. And I'm a coffee and a beer snob. So that was one of the asks for the bar downstairs. They need to have not just beer, but also good beer. And I believe that they're delivering on that front. So I went through a whole bunch of different ways to try and kind of lead into what I'm doing, try and explain it to in terms that a lot of other people can kind of start with the same kind of frame of reference. So what I looked at here was playing with Legos with my 4-year-old daughter who loves them. I love them too. It worked. And what you're seeing here is how there's all the different blocks that you can build something out of. And you'll see that you've got 5 different types of constructions here. And then you can show the different components that were used to build this. So when I look at a program, basically a program is just a collection of different functionality that you want it to do. So if you want a program to, I don't know, to take information from your bank account or whatever, and show you your account info and all that stuff, then you have to have like user input functionality and all those things. You have to cobble it together from little tiny pieces that do work. And many of you who are in the software field, that's probably second nature to most of you. But trying to piece it together is I got to build, in order to make a person from Legos, I got to build it out of these 3 parts. So I got to go into the bin, pull these 3 parts out. If I want to build a lamp out of Legos, I got to pull these parts out, etc. So this kind of covers, what I was talking about. And I think one of the key pieces that a lot of people miss when we're talking about malware is this laser pointer doesn't show up. So I'm just going to stick it right there. This last piece right here is the key principle that I like to impress upon people, is that malware is basically software. And in a lot of cases when we're seeing attackers using malware, there are a lot of cases where some of it will be stuff that was built for the purpose of using it badly. Some of it is built for some other purpose and they just happen to be using it in a bad context. And in the end, we can use all the same type of software analysis and software, like all the same software development principles that go into building your banking software also goes into building malware. And even a lot of the same user interface constraints that go into driving malware is the same user interface constraints that go into driving your banking software, that type of thing. So what I pulled together here is some of you who read like a lot of FireEye and all that stuff might know these these like 3 backdoor names that are talked about there in public source. So what I did is I kind of grabbed these as like a representation of my library, and if I pull one out, it's a backdoor, right? And since it's a backdoor, what it needs to do when it's installed on your system is this backdoor needs to provide, the goal is to provide an attacker with access to your system over the network. So in order to achieve that, the constraint that it has to operate within is that it needs to have, and I just kind of grabbed a subset of the functions here, it needs to implement network connectivity functions. So it, where some software may not need to do that. But in this case, in order to provide the attacker with that information, the author of this backdoor had to put in network code. So code for interacting with the network layer of the system. If they want to evade detection, that type of thing, they may have to also implement, say, encryption code in their program. So they'll have to grab the blocks and put them in the program to make an encrypted network traffic, that type of thing. And so the fact that they have stuck, in this case, network code in the program means that I can already select what are my backdoors among the set of programs that I have in my library that implement network connectivity functions. So those are where all my backdoors are likely to live. Likewise, the backdoors that attempt to evade detection, those are the ones that may implement network connectivity functions, as well as encryption functions, that type of stuff. So the question here is, how do we identify what are encryption functions, or even what are just encryption loops within functions? So when I get right down to it, and I come from a computer science, computer engineering background. I graduated from the engineering school here. Compiler, theory, lexical analysis, that type of stuff. Those are my bread and butter when I was in school here. So I come with a large amount of that knowledge. And generally when you're building a function within a program to accomplish a body of work, what you're really doing, say conceptually in the business world, is you've diagrammed out a flow chart. And that's what I've got here on the right-hand side of this slide. That's my flow chart for the decision tree that you would take to run the get file function. And so say that function implements functionality for an attacker to retrieve one file off of the hard drive of a compromised system deliver it over the network so that the attacker can have that file if, for instance, they want to steal your PowerPoint slide full of cat pictures. Very precious stuff. So each one of these steps in the tree, or I should say in the decision tree, are basically small little operations that occur at each level of that. So some work is done, a decision might need to be made, and then a branching path, and you can see that in the second one, may be taken based upon what the outcome of that first block is. And so here I break it down further, and now we get into the assembly language part. So these are real x86 instruction codes. So all your Macs, most of your Macs, unless some of you have those old PowerPC Macs, and all your Windows boxes run programs that are written in basically the same language in the end. So this is the native machine language. And what it is it's just a list of instructions where the processor starts at the top and it does something, and whatever the interaction is required of it causes changes to occur in memory. And then it moves on to the next line, and the next line, and the next line, so on and so forth, until it runs into a very small handful of special functions, or I should say special opcodes, like this one, call, which are going to tell the processor to jump to a different memory location. So go here instead of going to the next line. And that's how this decision tree logic that's built right here, that's basically how it's built in program code, is that you'll have these branching instructions that set up where your edges are on the graph. And so you can use that to delineate each one of these blocks. So instead of just having one long screen full of disassembly, I can use that, those branching instructions as points to break my code up into discrete blocks. And this is really important. This is the first step to what is called decompilation. Because generally when you're writing software in a programming language like C, you typically implement this with like the curly braces, or if you're a Python person, you typically like to implement this using the indentation and scoping, that type of stuff. All of that stuff gets converted into this type of construct in the code. And you can you can work it all the way back to what your individual blocks of code originally looks like. And so then, instead of having a screen full of disassembly, I now have a bunch of individual pages of disassembly of individual blocks of work that implemented some small tiny algorithm at each one of these that then some decision has to be made from. And I want to try and identify the functionality of each one of those little algorithms that's being done. So I'm going to just take that one that I carved out of there, and I'm going to walk through it a little bit to show what my mindset is on this. And one thing I've learned from doing this is that I don't need a perfect heuristic. Like, I don't need to build a perfect answer for this. I don't need to be right 100% of the time. I only need to have something that is effective most of the time in order to give me the ability to find my bad code. So what you'll see here is on the left-hand side, each one of those is action to be taken. So it's like your verb in your English language. And then on the right-hand side, it'll be a list of objects that that verb or that action is supposed to be taken upon. So you'll see that there is and actually on line 4 there, it says move, and that's supposed to be mul for multiply, a mathematical operation. I messed up my slide. I hope you'll all forgive me for that. But you can see it over here on the right-hand side. So the idea there is that move instruction, that's how you, that's assignment. So if you say A equals 4, that's what your move is there. And LEA is kind of a, we'll get into that later. That's kind of a similar type of approach using some internal math, push or stack operations, et cetera, et cetera. So you go down here and you have to do each one of these actions on the objects that are listed to the right. And so you'll notice at line 3 and line 4 right there that they actually have a common object that they're operating on. So that's basically do something first with that object, and then whatever the result of that operation was, move on and do something else with it after that in response to it. So you kind of have this data manipulation, data moving that you implement almost as if you're like a second grader trying to do multiplication by doing multiple additions in a row, that type of thing. That's what your CPU is basically designed to do, is to do small, simple operations very fast and do many of them at a time. So what I decided to do was I wanted to identify or think of how would you come up with a way to describe a block, its behavior, without falling victim of to the habit of having the different objects that are being acted upon impact that decision. And so the quick answer for me, because I like easy answers, was how about if I remove all the objects and just look at it from the perspective of the sequence of actions that are being taken. So in this case, and as I said, line 4 is a defect in the slide. If you just change that to mul, which means multiply, that's important in a second. Multiply is an arithmetic operation, so it's basically take two numbers, 3 and 4, multiply them together. Hopefully you get 12. Most processors these days will get that right. And then I just strip my, so now I've been given a list of action sequences that are taken. Those action sequences then give me kind of a behavior on this block of code. And live in different spaces in memory in other programs. Though when I run this analysis on those other programs, I'm getting the same result. So for the same algorithm, no matter where in memory those objects that it's supposed to be operating on might live. And that's kind of the key, that's the key benefit here, is that I want it to work such that when I generate output from this analysis, that no matter where the author put that block of code, or no matter where their data structures live, or even, in this case, no matter how those individual data structures, their layout may change over time, I still get the same result. So the description that I'm using here to describe the block ends up being the same output. And again, it's not going to be perfect, and we'll get to how you would deal with like failure cases and success failure. So as you'll see, the multiply operation is correct in this slide. This is basically how I take each one of those, because the other thing too with the x86 architecture is that there are an immense amount of different opcodes, different operations, different verbs in that architecture. But a lot of times there may be 10 of them that do basically the same thing or very similar things. They just happen to maybe differ on the types of data that they will work on, or possibly some minor side effects that don't really matter. Or in some cases, they may behave slightly differently just because one version of it runs faster in a certain context than another version. And when that type of distinction occurs, a lot of times that's where your compiler optimization, that type of stuff. If some of you are familiar with software engineering, setting that -06 modifier on your compiler will start to aggressively attack some of these instructions and find faster running, say, hacks in some contexts. So one of my other goals with this approach is to try and overcome some of those changes too. So what I did in this case, I created, my first heuristic was, again, an easy button. It was, I looked at the x86 instruction set, I said, well, in many cases, the first letter of the instruction ends up being ends up grouping them pretty well. Not perfect, but pretty well. So I'm just going to do that and see what it gets me, because I wanted to really quickly get to the point of generating data, generating results, and then being able to count how many times that it got the answer right versus wrong. So when it had an unknown sample of malware and a known sample of malware, how many times did it properly identify this after review? So you'll see what I did was I separated them into the M group, the L group, the C group, and the P group. And despite all the different instructions I have up there, there really were only 4 groups. So that's the other thing too here is this is a reduction in my a reduction in my language set. So I've gone from, I think there's 10 up there or something. I've gone from like 10 lines to now 4 lines of significant data by grouping them this way. And one of the interesting things is like this right here. As I said, these are 2 stack operations, which I won't go into explaining what the stack is. Suffice to say that it is integral to how most of your processors work. And there are 2 major operations that operate on it. So, but again, it's a simple, stupid heuristic that actually worked pretty darn well the first time I wrote it. So applying that to all of the instructions that I have in there gives me a list of letters, basically, of which ones are my groups. So then how about if I take those letters and then I just turn them into a string, and then I call that my position independent code block hash. And it's a string, it's an ASCII string, which means I can print this out on a piece of paper, I can put it on a website, I can put it on a PowerPoint slide, and it's actually readable by all of you. And since I've gone through the steps here, you actually have a pretty decent idea of how it looks. The other thing that's really cool is that there are a lot of software libraries out there and software programs out there for doing analysis on ASCII strings, for instance, for doing similarities for language analysis and things like that. So they'll give you like similarities of like if this P, so if this P is different in another block hash, that ends up being a 10% difference. It can actually give you those differences and allow you to get a little bit more fuzzy with the hashing algorithm. So that's the other thing that's nice is that I don't have to write any of those algorithms to do the comparison. I can just borrow them from something else that was originally written for a different application. The other thing that's really neat is that I can store all these things in a very efficient representation in known data storage applications like SQL databases, things like that, which would have been a pain in the ass for me to try and dump a large block of binary code into. I can do that here. I can build indexes on them. I can search for things in them. I can hook all my malware samples in my entire library up to that index tree using existing software instead of all writing it myself. And that's the beauty of it is once I represent this in a manner that's actually more common to how a lot of existing software works, then I can just take a whole bunch of existing software and apply it to the work I'm doing. So right here what you've got is I repeated that algorithm for every single one of the other blocks in my function. And again, this was the C2 get file function. So you might have, that top block might be the code for going and retrieving the file from disk. The second block might be copying it to memory. The third block might be connecting out. The fourth block might be sending. And the last block, maybe you would call that closing the connection, shutting down the connection. So I'm going to step back out again, and I'm going to do it for all the other functions. And pretty soon, I have a giant pile of data right here. And that giant pile of data gets even bigger when I start to look at all of the other malware samples I have. As you'll recall on the first slide, I had picked out 3 backdoors. I've collected way more than 3 backdoors to do analysis on. And so I've got an enormous mountain of data. So now we have a mechanism that we can script, we can hook up to a tool chain, and then we can just do my favorite part of the game, which is collect all the things. And some of you might be familiar, I handpicked many of these, so some of you might be familiar with what some of those represent, but we've got Poison Ivy and Dark Comet, Tomato Garden, Creepy Koala. I got that one in there for you, Nate. So get back to good intelligence program is really an effective data hoarding program. And what I like here is that I can go on the internet, or I can go on some of our users' machines, or maybe some machines that are on the guest wireless or whatever. I can collect the malware samples that are, say, submitted by AV or something like that. I can collect them all. I can submit them to my system. My system will run that algorithm through all their functions and all their blocks of code. And it will store in the database that was originally designed for doing a lot of kind of string-based analysis and everything like that. It'll store all those block hashes. And it'll relate them all back to these samples and the context around the sample. When did I get it? Where did I get it from? Who did I get it from? What else were they doing at the time? Anything I think might be of significance, I can kind of keep tying into it. So that's the crux of it, is can I get to a place where just submitting all of these malicious artifacts, all of these malware samples, can produce the data set, this one, and I'm actually going to go back here, can produce this data set and keep growing it and keep growing it and keep growing it. Because then what I do, so I'm building in a relational database, building relationships. If there are 5 malware samples that have these 2 blocks in common, that's going to be a really easy query for me to do in a relational database, which is where I get to this. So I'm not responsible for this, and I don't think he was able to make it, but Jeremy Humble is actually the guy who told me about this, introduced me to this, I should say, opened my eyes. And it's basically using a very simple algorithm that's called a distance, Jacquard's distance algorithm. And basically what it is remember how I showed you on there that I have a large list of blocks? I have all those block hashes, so all those unique block hashes in each one of the malware samples. So what I can do is I can take what I call the intersection of those two. So that is, like I pointed out before, there were maybe 20 blocks, and there were 2 of them that were common between multiple samples. I can put a 2 in the numerator of this little division thing. You're all familiar with division, right? So I can put 2 in the numerator, that's the top one. And then I can put, say, I said 20, right? I can put 20 in the denominator down there. And so what that's going to give me is that's going to give me 2 over 20, which is 1 over 10, right? And that means 10%. There's a 10% overlap between those malware samples. Jacquard's distance, what it does is it says it's a computation for how far apart 2 things are. So how far apart 2 things are, and it's used for plotting things on really pretty graphs. So what I'll do is that's the similarity what I gave you, the 10% similarity. 10% of the things overlap in both samples. So the difference between them, the distance between them, is 1 minus that. And that's going to give you 90% distance between them, those 2. So they're going to be 90% of the width of the graph away from each other if you were supposed to draw them. And we'll get to that. So, and then this is just intersection divided by union of sets. Intersection is your numerator, and then the union is the denominator. So this is the tables I set up for this. I'm not going to talk to all of this stuff, but there are 3 tables, right? The malware table, that's where I make unique IDs for every one of my MD5s and my malware samples. What I call my DNAs, or DNA strings. That is the actual string content of each one of those block hashes. I give it an ID as well. And I do this because comparing integer values to one another in SQL is a lot faster than comparing string values to one another. And then finally, that was another tip from Jeremy, by the way, who has all the pro tips when it comes to hacking stuff that shouldn't be in SQL in SQL. And then finally, the DNA relationships, which is a table which is only comprised of the ID values and none of the actual data values. And then using the fancy join logic that exists in SQL, you can have it do the math for you and give you the results by first narrowing the sets down by IDs. So what I did was I put together a really simple select query to try and do this math for myself behind the scenes using the database. And the benefit from that is that my workstation has like a measly 8 gigs of RAM or something like that, and the database server has, maybe 128, maybe a terabyte of RAM, a lot of RAM. And so if I fork all of the table logic, all the relational logic over to that thing, number one, it becomes the network ops guy's problem. And number two, it can actually be done without going to swap first. So what I wanted to do was calculate the distance function, which again is supposed to be intersection over union. So similarities over my total geography or over my total data set. And when I was doing the math, I came up with a very simple SQL construct to say the intersection is what I listed as T and U up here. And so T is the count, again, in that little DNA relationships table, we're going to be able to, we have a relationship between all the DNA IDs and all the malware samples. So if we just do a count on that, selecting where either one of the malware samples existed, what we're going to do is effectively get all of the things that were in one or the other, plus duplicates in the case where they were both in there. And that's where my count intersection plus union equals T comes from, is that count is going to be duplicating rows for every single one of the DNA strings that existed in both samples. And then outside of that, it's going to give me one row for anything that was only in one of the samples. And then finally, count distinct gives you the union, right? That's going to give you exactly what was in both of them. And so then we're able to use this to draw pretty pictures. This is the website, multi-dimensional scaling in Java. You may just want to write that down as very efficient. I went everywhere, and I know I made the crack about Java earlier on in the slide. This guy actually writes good Java code, which I found is a rarity. And so I recommend this. I tried for a long time to get R to do the work for me, and this does in minutes what R did in days. And so if I zoom in here, what I've got is colorizations on this chart for malware samples that I've already analyzed. So every single one of those dots on here, I already did a human review of those malware samples. And as you can see, I do a lot of looking at malware samples, which might explain my sense of humor sometimes. So a lot of these orange ones here that are in these little clusters, those are Ghost backdoors. Many of you are familiar with Ghost. It was publicly released. The Ghost wasn't officially publicly released, but it was publicly released that the Ghost 3.6 source code had been leaked out into the public sometime back in 2009 or 2010 or something like that. As a result of that, a whole bunch of people picked it up because it's easy to build, and it's C++, and a lot of people know C++, and they started hacking their own customized versions of it. So you can see that trend occurring here with all these little kind of clusters of Ghost backdoors. Then another malware sample that I call Smarty, that's done by a known actor that we track that writes their own malware. So they don't leak their malware to the public. They have a really tightly, neatly packed cluster there in the middle. And I've been analyzing that one for a really long time. And then finally, another malware sample that after I charted this out, I didn't even know it was there, are those two that are way out there on the side by where it looks like it's taken a big bite out of it. And that was actually called a UEX watch. And it looks like it's almost like a VM type of malware sample. So the code itself is written in a bytecode that was designed by whoever authored that malware sample. And then it executes the bytecode from a virtual machine that's implemented that rarely ever changes. Because anytime someone wants to change the features of the UEX watch malware, they just modify the virtual machine code, and they don't touch the code that I'm looking at, which is the bare metal machine code, the x86 instructions. And then finally, I can also use this to explore further interesting things. So there are 17,000 and some odd dots in there. This gives me a nice little way of saying, how about if I draw a square around the samples that are marked off by that blue line, and then have it give me the, say there's 200 samples there. Have it yank those out of the system, put them in a folder, and I'll go and analyze those 200 instead of analyzing all 17,000, right? And that's kind of what we're getting at here. So the other thing that I found was really beneficial for this is that if I can run this algorithm on malware samples, and as I said earlier, malware samples are just software. So there's nothing special about them. There's not like some malware compiler out there that has its own magical badness features to it. Most of the malware we see is written in C++ and written in C. Some of it's written in Delphi, unfortunately. But so is a lot of the software that we find on endpoints and that we install onto machines, especially custom software written for doing special manufacturing things. How about if we make a separate database where we collect all those things in, run all those things through the exact same algorithm, and then create a benign list of block hashes. So these are what good code patterns look like. If some of you are familiar with building software, like any of the stuff you guys might have done in a software engineering course, what comes out the other end is usually 10% what you wrote and 90% what some dude at Microsoft wrote, who wrote the original libraries that provide all the support functionality. So I can build this benign data set to help me eliminate the, or I should say provide access to me to a filter of block hashes that I can safely ignore from an analysis standpoint. So these are the blocks of code that I do not want to focus on to try and find what's the unique badness in this piece of malware. I built a lot of detection as well. And to do detection, you need to search for the characteristics that are unique and identifiable about malware. Having a benign data set on hand allows you to run your, say, this algorithm, run your malware against that benign data set, and out the other end comes the 10% smaller, or I should say, the 10% of the haystack where your needle is likely to live. So the other thing, too, that I can do from this, and like I was showing you on this chart, is that if I upload a new malware sample and its dot happens to live right there after all the analysis is done, after a half-hour analysis runs, what does that tell me? It's probably ghost. Thank you. So what I can do with that is I can give immediate feedback to people. I can say, hey, you know what? When you submitted that thing, that looks like 99% confident that it was ghost because of our history on running the algorithm. Whenever it finds it as ghost and it lands there, that's been 99% true after review. So we can tell people that. We can put a ticket so we can create work for someone else to go and do. We can highlight useful analysis work that might be available for someone to do. So rather than having people waste time searching for work to do, we have an automated way to try and identify the most beneficial places where they should go to do work. And then finally, my favorite is filtered block level disassembly. So in addition to hiding from my eyes all of the normal Windows library code that's going to be living in my malware samples, that if I were to write a signature against those pieces of code, it would match on every single program on my system. If I've already analyzed 5 pieces of malware and I have determined they are all part of the same family because I'm a human analyst and I spent 5 hours doing that, driving myself crazy, then I can basically run the same intersection logic on all of them and find the 2 or 3 blocks that exist in every single one of those malware samples. And some of the other blocks may change over time as they modify an encryption algorithm, or they add an extra step to, say, the network connection, or they they add one more feature that stores more information about the user. So maybe they add a password scraper or something like that. You know, these will be slight changes to the code base, but there's also going to be all this code that lives on forever. And I mean, I've been doing software work for a long time, and bad code lives on forever, especially horribly unreadable code. And that is, from my experience, no different when it comes to malware samples and malware projects. And that is a key place to do this last filtered block level disassembly, which I can actually have it show me the disassembly of the 2 blocks from, say, 1,000 blocks that are across these 5 malware samples that occurred in every single one of them. And those are the ones that are going to pinpoint to me where I want to apply work to build detection signatures around them. Because for some reason, I don't know what the reason is, but for some reason, they seem to be very resistant to being changed by the author. Possibly some critical functionality to the backdoor that even the current maintainers of that malware may not exactly know what it does. Raise hands for me of anyone who has inherited code that has components in it that you have no idea what it does. Yes, we've all had that. So this kind of gets to just like, I like to track a lot of the work that we do, track a lot of the collection, partly because my employer forces us to do that, but also because it helps me gather kind of success and failure, gather how good the program's working, right? So I threw some stuff up here, and this is definitely not an all-inclusive list here. You can come up with everything that you just kind of pick and choose measurements that you can do every single day to figure out how to tell yourself if the program's working, if it's not working so well, to clue yourself into the types of improvements that could be made. So in this case, I can give the reference benign data set size. That can indicate to me over time, since I'm constantly collecting new good things that look suspicious at first, turned out to be good, I'm constantly collecting those and adding them to the system. That's going to give me a growth plan for my storage on my analysis server, that type of stuff. Same with the number of samples, EXEs, DLLs. You can also get clued into if some aspect of the program broke and you're no longer collecting new samples. So you can do all sorts of things like that. Then what I have is one of my favorite things is the auto classification dashboard. And so like I said before, when you upload the sample and the sample goes onto that graph and it happens to be dead center in one of those known malware type sections. So these are, I think there's like 25 up here or something like that. These are a bunch of different threat groups, I would say, that we track. I've listed them all up here with everyone's favorite TV show names. Forgive me if I left your favorite character off. They were just not my favorite character. And what you can see here is over a month of time that people have just been collecting malware, and the people who collected malware, they had no idea where it was coming from. They didn't put any special collection plan around it or whatever. They just saw like a report that said, hey, this stuff's bad, and they can go to VirusTotal and get it, or they can get it from malshare.com or whatever. So thousands of samples were uploaded, and then this is, maybe there's like 500 samples up here or something, right? This is counts for each one of these groups what the auto analysis was able to do. So the auto analysis was able to identify at the moment of submission that that malware sample fell into like the carbon rod group, right? Inanimate carbon rod did not fit, but it's my favorite Simpsons character. So that's what I've got here. And so I can show month over month, not just what we're collecting, but what has been submitted. And that might be indicative of, say, the Carl group. Maybe that's because the Carl group got really, really active that month for some reason. Maybe we should apply some work, some resources, to trying to do more exploration of what their activities are, versus, say, the Barney group, which only submitted one sample. And it looks like it says -1. I have no idea how that stray thing got on there, but it's 1. I checked the data. So, I can run charts like this on a regular basis to get an idea of, say, what current trends are, what current activity is, and then you can chart each one of these out on a really nice graph. I do a lot of graphs, by the way. It's I don't know, it's just a obsession of mine when it comes to this stuff. And so I've kind of listed some since February 10th. So I think this chart was dated around April or something, so it actually covers about a month and a half. The other thing too is that when I'm doing each one of these things, a lot of, I create a new work ticket, so it's a review ticket. The system itself doesn't auto-identify things. The system itself doesn't automatically give me the answer. What the system does is when 5,000 things are being uploaded over a month and a half period, it pulls out the 500 things from that, the 10% of that it thinks that it has a really good opportunity to auto-classify for me.
5 minutes.
Okay. And that's really what you're seeing here. So I can go through each one of those and I can mark it a yes or a no. Did you get it right? Did you get it wrong? And using this exact same layout, I can determine how good am I at positively identifying carbon rod versus how good am I at positively identifying the Lisa group or something like that. I could generate a first time right. I can figure out for that algorithm which ones of these do I never ever want to see a work ticket open for, because 70% of the time it's wrong. I need to have a different approach to attacking that, that problem. I need to maybe apply the same analysis on a different data set from the malware, that type of thing. So I just talked to that, but enjoy the meme. And then finally, what I'm working on now, find a better opcode grouping. What I did up here, you know, the M group, I pulled these directly from the earlier slide. Maybe just using the first character isn't the best thing. Maybe we should group them by functions and then apply a discrete letter for each one of the functional groups of opcodes and get a better approach that way. And one example that I'll go through really quick is like add, subtract, and add with carry. That's that second from the bottom group there. A lot of times compilers will interchange those based on context. And that means the author wrote one thing, but the compiler did one of 5 things with that information. And you're really trying to get back at the patterns and signatures that the author has left in there. What's the author's fingerprint? And not all the authors, but just the bad author who wrote this malware sample. So, in closing, questions? Yes?
When you were looking at the distance between 2 samples,
Yes.
comparing number of blocks and the union intersection number, how did you determine the optimal size of a block?
I don't have an optimal size. I think I cut it off. I say don't show me blocks that are less than 1 or 2, but that's where my benign data set comes into place, is that any blocks that are too small end up showing up in all of the good software very frequently, and so they're immediately cut out of my data set. That's another thing too, when I'm doing these algorithms, I'm only comparing the subset of block hashes that did not show up in that enormous benign set that I have. So I'm only looking at about 10 to 25% of each of the programs, cherry-picked to be the stuff that's most likely what the author wrote. And that helps. Side effect is I also get that win too. Yep.
I see you split blocks at branch, jump, and return instructions.
Yes.
Anything else?
One thing that I didn't put in the slide here, but you should all write down, is a Rose compiler. So Rose like the flower, compiler, one word, .org. It is a decompiler and compiler. So it's originally designed to be a language-to-language compiler. So it would do something fancy like convert Python to C or something like that. One of the maintainers of it at Lawrence Livermore National Labs put together a he wanted to convert disassembly, so x86 bytecode, into C code. And what I'm using is their block separation algorithm, which is good that you brought that up, because one of the distinctions of their block separation algorithm that is different when you compare it to, say, IDA Pro and some of the other navigation tools, Rose compiler doesn't consider multiple jumps in a row. So if you have what we call spaghetti code, where it's 100 blocks of code with one instruction each that's just a jump, Rose compiler identifies, rightly so, that that's actually a linear block that's spread across multiple places. It crams them together for me as one coding pattern, and I can write a signature for that. I can't write a signature for individual jumps just spread all over who knows where. Does that answer your question? Sorry. Okay. I'm getting the hook, I guess. So I'll be around for...
Questions, so you can grab them from the
Yeah.